Assalamualaikum to Sir. Today I would like to present our RFIC project entitled Receiver Front-End Design for Wireless Communication. This project focuses on the design and simulation of a receiver front-end consisting of a low noise amplifier or LNA and a mixer using Cetera C18G CMOS technology. The purpose of the design is to amplify weak RF signal while maintaining low noise and converting the RF signal into a lower frequency for further processing. So I will begin the introduction of the receiver front end. For the second slide, a receiver front end is the stage of a wireless communication receiver. Its main component are the low noise amplifier or LNA and the mixer. The LNA is responsible for amplifying very weak RF signal received from the antenna while adding as little noise as possible. After amplification, the signal is sent to the mixer. The mixer combines the RF signal with the local oscillator signal and performs frequency conversion, producing an intermediate frequency or IF signal, which is easier to process in the next stage. Therefore, the receiver front end plays an important role in determining the overall performance and sensitivity of a wireless receiver. As for the objectives of this project are: first, to design a CMOS low noise amplifier using Cetera C18G technology. Second, to design a passive single balanced mixer. Third one, to integrate both the LNA and mixer into a complete receiver front end. Fourth, to operate the circuit at a frequency of 1.45 GHz. And finally, the design aims to achieve specific performance target, including a gain greater than 15 dB, a noise figure below than 5 dB, good linearity performance represented by IIP3 and P1 dB, and low power consumption.
Assalamualaikum, my name is Nabil. Next, I will explain the design of the low noise amplifier or LNA used in this receiver front end. The selected topology is an inductive rejection common source LNA, which is widely used in RF receiver applications due to its low noise figure, improved input matching, better linearity, and enhanced stability. The circuit was designed using Cetera C18G CMOS technology and operates at the target frequency of 1.45 GHz. Key design parameters include a 1 volt supply voltage, 0.5 mA drain current, 1 kΩ drain resistor, and transistor dimension of 80 micrometers by 200 nanometers. To verify their design performance, cadence virtuoso and spectral RF were used to perform DC as parameter noise and linearity simulations. This slide shows the determination of the LNA biasing parameters. First, the supply voltage was set to 1 volt to satisfy the low power requirement of the receiver front end. Next, the drain to source voltage or VDS was selected as 0.5 volt to provide distribution voltage headroom while ensuring that the transistor operates in the saturation region. Operating in saturation is important because it allows the transistor to provide stable amplification and achieve the desired RF. This slide presents the determination of the drain resistor and transistor dimensions. The drain resistor RD was calculated using Ohm's law based on the target drain current of 0.5 mA, resulting in a value of approximately 1 kΩ. The transistor width and length were selected as 80 micrometers and 200 nanometers, respectively. These dimensions provide a suitable trade-off between gain, noise figure, and linearity while maintaining operation at the target frequency of 1.45 GHz. Therefore, the selected parameters support both the RF performance and low power design requirements.
The next slide is inductive degeneration analysis. One of the key features of our design is the use of source degeneration inductance. The purpose of inductive degeneration is to improve three important RF characteristics. The first one is input matching, noise performance, and linearity. Through small signal analysis, we calculate the input resistance to be approximately 167 ohms. However, this theoretical value does not account for practical effects such as parasitic capacitance, interconnect losses, and device loading. Therefore, optimization through simulation was required. Using cadence spectre RF, we optimized that gate inductor LG is 8.3 nanohenry and source inductor LS is 7 nanohenry. This value successfully transformed the input impedance towards the desired 50 ohm matching condition. This is important because maximum power transfer occurs when the source and input impedance are matched.
For this slide, it presents the gain loss figure and input return loss performance of the proposed LNA at the operating frequency of 1.45 GHz. Based on the simulation result, the LNA achieved a gain of 29.89 dB, which exceeds the required specification of 15 dB. This indicates that the LNA is capable of providing sufficient amplification for weak RF signal. The achieved noise figure is 2.49 dB, which is well below the maximum requirement of 5 dB. This shows that the LNA introduced minimal additional noise to the received signal. For input matching performance, the input return loss S11 is negative 16.54 dB, which is lower than required negative 10 dB. This indicates good impedance matching with a standard 50 ohm source, resulting in reduced signal reflection at the input. Overall, all RF performance specifications were successfully achieved at the operating frequency of 1.45 GHz.
So, for input 1 dB compression point. Now I would like to discuss the input 1 dB compression point or 1P1 dB, which is one of the most important parameters used to evaluate the linearity performance of an RF amplifier. Ideally, an amplifier should have a perfectly linear relationship between input power and output power. This means that if the input signal increases by 1 dB, the output signal should also increase by exactly 1 dB. In practical circuit, transistors have physical limitations. As the input signal become larger, the transistor begin to approach its nonlinear operating region. At this point, the output no longer increases proportionally with the input. The 1 dB compression point is defined as the input power level where the actual gain becomes 1 dB lower than the ideal linear gain. It marks the beginning of noticeable nonlinear behavior. The first region is the linear region where output power increases proportionally with input power. The second region is the compression region where the curve starts bending downwards because the amplifier can no longer provide constant gain. From our simulation result, gain compression begins at approximately negative 16.52 dBm. This value represents the IP1 dB of our LNA. This result exceeds the required specification by approximately 8.48 dB, indicating that the amplifier can handle stronger input signal before significant distortion occurs. This is important because wireless communication systems often operate environment containing signals of varying strength. A higher 1P1 dB therefore provides better dynamic range, better signal integrity, greater tolerance to strong incoming signal, improve overall receiver reliability. So, the next slide is input third order intercept point, IIP3. Now, the input third order intercept point or IIP3, which is an important parameter used to evaluate the linearity of an RF amplifier. In wireless communication system, the receiver often receives multiple signals at the same time. Due to the non-linear characteristic of transistors, the signal can interact and generate unwanted frequency called intermodulation distortion products. Among these distortion products, the third order intermodulation products are the most critical because they appear very close to the desired signal frequency. Since they are close to the wanted signal, they are difficult to filter out and can reduce the overall receiver performance. To measure this, a two-tone test is performed. Two closely spaced frequencies are applied to the amplifier input, and the output spectrum is analyzed. From this analysis, both the fundamental signals and the third-order distortion component can be observed. The IIP3 value is obtained by extending the fundamental signal line and the third-order distortion line until they intersect at a theoretical point. Although this intersection does not physically occur, It provides a useful indication of the amplifier linearity. So for our design, the simulated IIP3 is negative 6.15 dBm, which is significantly better than the required specification of greater than negative 15 dBm. This result indicates that the amplifier has good resistance to third order distortion and can maintain signal quality even when multiple signals are present simultaneously. In practical wireless communication application, a higher IIP3 means better linearity, lower distortion, improved receiver performance, and great reliability in crowded RF environment. Therefore, the achieved IIP3 result confirms that our LNA design meets the linearity requirement and is suitable for wireless receiver from an application.
For system architecture, the slide shows the overall architecture of the proposed receiver front end. The design consists of two main blocks, which are the inductive degradation common source LNA and the passive single balance mixer. The signal flow begins at the RF input where the LNA receives and amplifies weak RF signals. The inductive degradation technique is used because it provides low noise figure, better input matching, improved linearity, and enhanced stability. The amplified RF signal is then fed into the passive single balance mixer. The mixer performs frequency down conversion by mixing the RF signal with the local oscillator signal, generating an intermediate frequency output. Overall, the complete receiver front end operates at 1.45 GHz and is designed to achieve high gain, low noise, and good linearity performance.
After determining the design parameters, the receiver front end was developed following several design stages. First, the transistor balancing conditions and device dimensions were established to ensure proper operation at the target frequency. Next, the input matching network and inductive degeneration technique were implemented to improve impedance matching, noise performance, and linearity. The design LNA was then integrated with a passive single balance mixer to form the complete receiver front end architecture. Finally, cadence virtuoso and spectra were used to perform simulation and evaluate the overall performance of the design. Now we move to conversion gain result. This slide presents the conversion gain performance of the proposed receiver front end. Conversion gain is an important parameter because it indicates how effectively the receiver amplifies and converts with RF signals without further processing. Based on the simulation result, the receiver front end achieved a conversion gain of 18.88 dB. This result exceeds the project requirement of 15 dB, demonstrating that the proposed design is capable of providing sufficient amplification. Therefore, the achieved conversion gain confirms the effectiveness of the LNA and meets the integration at the target operating frequency of 1.25 GHz.
DSB noise figure result. This slide presents the DSB noise figure performance of our receiver front end. Based on the simulation result shown in the graph, the achieved noise figure at the operating frequency of 1.45 GHz is 4.754 dB, as indicated by the marker on the curve. This result successfully meets our design requirement of less than 5 dB, which is an important target for RF receiver application. A low noise figure indicates that the circuit adds only a small amount of noise to the incoming signal. This helps preserve signal quality and allows the receiver to detect weak signal more effectively. Overall, the result confirms that our LNA mixer receiver front end achieve good low noise performance and is suitable for wireless communication application operating at 1.45 GHz. Linearity performance. The linearity performance of the proposed receiver front end based on two important parameters, which are P1dB and IIP3. From the result on the slide, the achieved P1dB is 24.67 dBm, while the IIP3 is negative 6.1.5 dBm. Both values exceed the required design specifications, indicating that the receiver front end has good linearity performance. The P1dB results show that the circuit can handle relatively high signal levels before significant gain compression occurs. This means the receiver can continue operating effectively even when stronger signals are present. Meanwhile, the IIP3 result indicates good resistance to third-order intermodulation distortion, which helps reduce unwanted signal interference and improve overall signal quality. Therefore, this result demonstrates that the proposed LNA mixer receiver front end provides a good linearity, strong signal handling capability, and reliable performance for wireless communication application. Performance summary. This slide summarizes all major performance results. The receiver front end successfully achieved for operating frequency 1.45 GHz, conversion gain 18.88 dB, noise figure 4.754 dB, IIP3 negative 6.15 dBm, and last one is P1 dB 24.76 dBm. Comparing this value with the design requirement shows that every specification was successfully achieved. The result demonstrates that the proposed LNA mixer architecture provides high gain, low noise, good linearity, and low power consumption. This characteristic make it suitable for modern wireless communication system. So the last slide is conclusion. So for the conclusion, we successfully designed and simulated a CMOS receiver front end using Silterra C18G technology operating at 1.45 GHz. The design combines an inductive degeneration common source LNA with a passive single balance mixer. Simulation results confirm that all design specifications were achieved. The circuit delivered 18.88 dB conversion gain, 4.754 dB noise figure, negative 6.15 dBm IIP3, and 24.76 dBm P1 dB. This result demonstrates that the proposed receiver front end offer excellent amplification, low noise contribution, and strong linearity performance. Therefore, the design is highly suitable for wireless communication receiver applications and provide a strong foundation for future RFIC implementation and fabrication. Thank you.